Hi, Dave Allwell again. I'm doing Lab 6 for you, walking through it. I'm sorry this is late. I was extended involuntarily at Newport for this command inspection, and I've been sick. I got back late and I'm behind. Sorry about that. So Lab 6 is kind of important. We're going to walk through some skills. Some of these skills will be necessary to efficiently do the homework. Others are just nice to have. I'll try and run through it fairly quickly. You can see the objectives listed here, which is to construct a spreadsheet, FMIA and FMICA, then to use a spreadsheet to analyze a reliability block diagram, and then analyze a fault tree and a reliability block diagram using commercial software. And last, the fifth one's really easy. It's know where you can get training on the Reliasoft products above and beyond what I'm going to provide in this short lab. They have a selection of videos that's listed in the references. All right, so let's begin. So the example we're going to use is for a ballpoint pen, looking something like this. It has a plunger, a clip, an ink stick inside. Well, you can take it apart and break it. An ink stick inside, a spring, a couple other simple parts. And the context of the pen is not important. It just gives me something to work on. So the components I'm going to consider are the plunger, the ink stick, the spring, the body of the pen, and the clip. The plunger is going to say it has a single failure mechanism due to wear. We'll say the ink stick can fail two ways. Either the tip can break or it can run out of ink. Spring will say has a single failure mode due to metal fatigue. Body can break from shock if I drop it, or if I set it on the heater, it can deform from heat. And again, the clip can fail either due to fatigue or operator error. I like to think of my kids breaking it off just for something to do. So we're going to organize a simple spreadsheet, which you see on the right. So I put in the components for each. Some components only have one failure mode. Some components have the two failure modes. I just laid it out as a table. And then I've got to put in the severity, likelihood, and detectability numbers. For the pen here, I'm just making it up, approximately right. For doing an actual analysis, you would have scoring criteria that would say how you get the numbers from 1 to 10 for severity and for likelihood for detectability. And the big challenge to doing these FMIAs is to have a good enough criteria that can be consistently applied. But for the purposes of showing how this works, I'm just making numbers up. So I said that if the plunger fails, that's a severity of 5 on a scale of 1 to 10. It's not very likely, so it's down to 2, and it's easy for me to detect, so I gave it a low number. The product of those three numbers is 20. That's my risk priority number. For the ink stick, if that breaks, then I get ink all over me and my shirt gets bad, which happens to me all the time. My wife gets annoyed. Okay, if my wife gets annoyed, severity is 9. That's a big deal. Okay, and then for the likelihood, and it's easy to detect, I have ink all over me. Okay, so the product of those three numbers is my RPN there, risk probability number. Again, for no ink, similarly, for metal fatigue, if the spring doesn't work, the pen's hard to operate. That seems, from my experience, to be the thing that usually breaks. And it's hard to see that the spring is about to break until it does break, so it's low detectability. So the product of those numbers gives me 150, and so on and so forth. I filled out these numbers. So the point is that the top three failure numbers now, when I look at this column here, the spring is the biggest one, followed by the ink stick, tip break, followed by no ink. And so those are the three highest scores on the system. So those are the first three things I would look at to try to mitigate. And although I don't have it here, one could put in a mitigation strategy. If I can type here, make this word wrap text, okay. And it might be for the spring, I might use higher quality steel. Make this word wrap on all of them. And then if I did that, that might make the likelihood of it breaking drop down to a 2, and then updated okay, so if that dropped this likelihood down to 2, then I have 5 times 6 times 2, which should only be 60. 60 for my new risk priority number. and so on and so forth. And I could maybe have a clear case to make it more detectable. It doesn't really matter. What this is it's a management technique for keeping track of the various things that can go wrong. And it's a design for reliability tool because I haven't actually made the pen yet. I'm thinking about the pen ahead of time before I built the system and put it in. And so it can be used to help me drill in on the items that I need to think about in my mitigation strategy before I've committed a lot of money to making the items. Similarly, we have this failure mode affects criticality analysis. It's the same general idea, except that instead of using these severity, likelihood, detectability, ordinal scoring methods, we try and use something a little bit numerical. So we do the likelihood that the item is going to fail, what fraction of the failures are due to the different failure modes. These numbers have to add up to 1. What's the probability of system loss if the component is lost? And the product of those numbers gives me what's called the criticality number. And so you can see this printed here and done similarly on this spreadsheet. And again, I find that the biggest number I have here is a 0.09, which says that my, biggest number is 0.21, which says that running out of ink is my biggest problem, followed by the plunger failure at 0.16, followed by the tip break at 0.09. So another way to score, and again, I could put down my mitigating techniques and what the results of mitigation were. So, as I say in the lab worksheet, these are trivial examples, but they do illustrate the method. If you do get a complicated system, this can run to hundreds and hundreds of pages, and the management of it gets to be difficult. In the lesson, I showed an example from a commercial package of a sheet. It really doesn't matter what you do, the basic input's the same. It's just a way to lay the problem out, and it all's going to depend, the quality of it's going to depend not on the spreadsheet or on the software, but on how good the numbers are that you put into it and how useful the mitigation techniques are that you develop. Okay, so that's it for those two things. Let me stop for a moment. Okay, I'm back. Let's talk fault trees now. Fault trees you can do by hand on graph paper or scratch paper. You can do them in Excel, but it's hard because the symbols aren't there. Or you can use specialized software, which is what we're going to do here. There are commercial add-ons. You can Google Excel fault tree analysis, and companies will try to sell you packages and templates to do that. We're not going to do that. I figure you could probably do them by hand if you had to, but I did want to show how you do them with BlockSim. All right, so I've got a Windows emulator running here on my Mac in this window right here. I'm going to go to Reliasoft and start BlockSim. Takes a bit. And I believe you have BlockSim shipped with your licenses, and it's good till the middle of October. Okay, so I'm going to make a new repository, and I'm going to call this Lab 6 Demo, just for grins and giggles. All right, and I get a prompt like this that asks me what I want to do. Well, I want to start with an analytical fault tree to begin with, so I'm going to click on that. And then it pops up with an open screen. First thing I'm going to do, because life gets annoying, is I'm going to turn off this auto arrange feature, because I want, when I drag things and put them in place, I want them to stay there. All right, so let's think about the fault tree for the ball pen that we just did. So the top gate's going to be an OR gate, because it's going to fail if this, 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 or this fails. So let me add an OR gate, put it over here. And then if I go back up, I had two items that just were themselves events, and I had 3 more OR gates below it for my 5 parts. So I'm going to add my 2 events. Okay, and I'm going to add 3 OR gates. 1, 2. You don't go there. Let's see, and just to make this all easy, I'll slide this one over here, slide this one over here, and put another event in here. All right. Now under these the ink stick had two ways that it could fail, so I'll add that one and add another one too. Okay, and this shouldn't be an event. We'll come back to that. And the body had two ways it could fail, so I'm going to add basic event to that. And now I have to add one more of these OR gates here. Slide it over here. And it had two events with it, so add event 1, add event 2. Okay, so that's the basic layout. Let's go and label stuff. Come back down here. So if I click on the first one here, it pops open this window, and I can put what the block name is. So I'm going to put the block name, I'm going to erase that little thing there, and I'm going to call this the ball pen. Okay, and so that's the name that I now see on the screen. This is my plunger. So I'm going to name this plunger. And as long as I've got this open, I'm going to add the distribution for the failure rate, which I have here on the table. So I said that that's going to wear out, and I just made something up again for purposes of examples, a Weibull with a shape parameter 3 and a scale parameter of 200. I can also link this back to the Weibull++ data and fit a model with the associated uncertainty to a set of data and pull it into the software, but we're not going to be doing that today. Okay, so the model failure we set for this is going to be a Weibull two-parameter distribution, and the beta, its shape parameter is going to be 3, and the scale parameter is going to be 200. And units, days are fine. I think we're going to use units for days here, so I'll click that OK. So that is the characteristics for my plunger. Similarly, I can name these other gates and put their properties in, and I'm going to let you go ahead and do that instead of taking time to do that. So let me stop and pull up what the completed thing looks like. So this is what the fault tree looks like with all of the data put into it and everything labeled, with each of the distributions put into it. I want to show now how we can do some analysis. And I moved the events up and down because numbers are going to show to the left and right, and I want to be able to see it. Okay, so to do an analysis, I have to hit the little analysis button. And so when I do that, it's going to fit a model to the various to the fault tree. And then here, as I go to see my results, I can actually put some results in, and I can pick a time. Unfortunately, this is in hours, and we set it up to originally be days. I don't know how to change the default to be days instead of hours, and I'm just not willing to screw around with it today. So if I wanted to know for 20 days, for example, that'd be 480 hours. So I put 480 in here, and it tells me what the overall reliability of the system is and what the reliability of the various components of the system are based on the fault tree analysis. And I can also show the probability of failure, the unreliability, by refreshing that if I want to do that. Oops, hit the wrong type, I'm sorry. I don't want the plot, I want to go back to diagram. I can update it with to show the unreliability, and that comes in as Q's instead of R. Okay, so that's pretty handy. Again, the advantage of doing this stuff with software is it's a lot easier than doing it by hand, and it cleans up pretty nice. The plots that I'm interested in, first I want to take a look at what my failure rate looks like for this system, and that's what you see plotted here on the paper. Looks like it's concave down and then shifts to be concave up. It's probably not well modeled by a standard distribution, but we wouldn't expect that. I can also get other plots out of here. I can get the reliability versus time, which drops, and I can also get the plot of the PDF and a plot of the unreliability with respect to time. We're going to come back and do reliability importance, but I'll just say at this point, you can get the reliability importance plots here off this menu as well, either from a fault tree or from a reliability block diagram. They're logically equivalent. Okay, so how do I get over to a reliability block diagram? Okay, so for my fault tree here, if I go back to my diagram, I can go up to this button here. It says create reliability block diagram, and if I do, it takes this fault tree and it turns it into a reliability block diagram. It's not going to be very interesting because this is basically a series system. All these OR gates mean it's series systems. OR gates translate to things being in series, and gates translate them to them being in parallel. So I've already hit that button. Let's hit it again. It'll make me another one. And again, here is just my series system. But the important part of that is I can analyze that in BlockSim just as well. Calculate the model. I can go to the quick calculation pad here, and I can ask for what reliability is at the time of 100 hours, or what the conditional probability failures are, all the other things. Because I've put in the model parameters and they're not fitted by data, they're exact. So it doesn't make sense to get confidence bounds to talk about how much uncertainty is from the data because I have no data. But if I did draw these block properties from models, fit and reliable, and pull them in, they would inherit the uncertainty, and I could get confidence bounds for the overall system based on the uncertainty in my sample sizes. All right, so another example here. Here's a very simple block. We've got these four blocks, 1, 2 in parallel, and another one in series. Here's 4 distributions I made up for it, and I said we're going to look at the analysis of what it's doing at time equals 100. Let's take a look first at this in a spreadsheet. Okay, so I'm over here in a spreadsheet. Here I've got my 4 blocks. I've set my time here, and for the reliability for this, I've just said it's 1 minus the reliable distribution with the time here in block F7, and with the parameters 3 and 200, I put them by hand, and 1 for the CDF. So the reliability is equal to 1 minus the CDF, and the reliable distribution, exponential, and reliable again. Excel wants the rate, so I've got a 0.01 here as a rate. When I go to do this in BlockSim, I have to remember that BlockSim is parameterized by the mean, so I have to take the reciprocal, but it's not hard. Okay, then to do the analysis, first thing is I aggregate blocks 3 and 2 together to be 1 block, and so since they're in parallel, the reliability of that block is 1 minus the probability the first one fails times the probability the second one fails, so 1 minus these reliabilities. And that's the formula that I put in here. Let's see if we can see it, which is my reliability formula. And then to get the reliability of the system, then it's just block 1 times the aggregated block 2, 3 times block 4, and that gives me my overall reliability. And the nice thing about doing it this way is I can change the time. If I want to make it 50 time units instead, I can see how the reliability changes. And if I wanted to be really clever, I could probably plot it over time. Point is, I can do lots of distributions, lots of reliabilities, and do this. Sometimes what you get from the book, though, is they'll ask you, they won't give you the underlying distribution, they'll just give you these reliabilities. And if that's the case, you would just type in what the reliabilities were for fixed for whatever time, whatever mission time you're given. So I could put a 0.9 here, a 0.8, a 0.7, a 0.8, and a 0.95 here. Same idea, they're not calculated from the distribution, but the logic of the organization still holds the structure here, and it would give me my overall system reliability after calculating the intermediate block 2, 3 again. Same idea. Okay. I can also do this in BlockSim. It's not a big challenge. Let's see where I've got this one. I think it's this one. Yeah, so here's the block entered. I set the block properties same as I had here. So for example, block 1, I've listed it, I've named it, I haven't named it anything, but it's a viable 2 parameter with a shape of 3 and a scale of 200. Just like before, those are all entered in. I have this extra block here which I don't need. And once it's analyzed, again, I can analyze it by hitting the analyze parameter, go to my quick calculation pad, and if I want to find out what the reliability is at time 100, I put 100 in here, click calculate, and I get the same number I had in Excel. Again, not a surprise. All right, close out of this. So I've talked about this point about the static reliability. I mean, maybe I didn't. So let me just add another block here. Let's say I was making it where I was doing it at a fixed mission time, and the reliabilities at that time were all given to me. I didn't know need to get them from a distribution. So when I put the properties of that block in, when I go to the model reliability, if I click this little button here on the right, instead of picking a distribution, I can just put in a fixed reliability, 0.94 for example, and then that block always has a 0.94 reliability no matter what the time is for the other system, and I can operate on that just as well. That's handy for some of the program problems you're given if you're trying to do a block sim, because the book just gives the actual values, it doesn't give the underlying distributions. All right, let's see where we're at on this. For the graphs of reliability importance over time, let me go back to the first model I was working on. Right, okay, so if I do the plot of the metrics, reliability, importance versus time, for each of the different components, this is the graph of the partial derivative of reliability with respect to reliability components and how it drops over time. And in particular, you can see that this biggest one that I'm putting on is shock. Shock is always the most important component from a reliability perspective in this model. So if I want to make improvements to the system, costs being equal, shock is a good place to start. Okay, and here's the formula that does that. We can also do these in a spreadsheet example. Let's see where I have this. I have a different spreadsheet here. Bear with me for a moment. Is that the one I want? Yeah, bring this over here. So here is problem 17 done out with all the various different reliabilities listed. And I've aggregated A1 and A2 together, then the B's together, then the C's together, and I've done an overall system reliability based on that. So that this is, just the analysis of 17 itself. I guess I gave you the answer, didn't I? That wasn't very smart. All right, whatever. Do your own work anyway. But here I'm going to say, what happens if I change these reliabilities by a small amount, delta 0.001? And I've got this set up with an indicator variable to show which one I'm doing. Well, if I take 0.95 and I subtract 0.001 off of it, I get 0.949, that's my new reliability. None of these others changed. And I calculate what the new reliability of that system is after I've done that change, the exact same process. And then I take the change in the reliabilities, which is this number minus this number, and that gives me my delta, this idea of change in system reliability. And I divide by this change in the reliability of the component, which is 0.001, and I get the reliability importance. And I just copied and pasted that number up here, and I went through and did it for all the other ones. And you can see here, the one that has the biggest overall reliability importance is, it's a tie between, it's actually C4 and then C1. Those are the ones that make the, where a small change in reliability of those components has the biggest overall effect on the overall system's reliability. And so I'm just again trying to show that these things can be done with spreadsheets as well as block sim, if you know what you're doing. And taking these derivatives numerically, that's what this is a numeric approximation of this derivative, based on the fact that the limit of these two deltas, as delta goes to 0, gives me the exact partial derivative. That means I can do it without having to know any calculus at all. I just have to understand what's going on under the hood. All right, so that's pretty fast. But those are the main things for what I wanted to do this week. I would like to next week maybe show an example of how to do a cost calculation, allocate reliability when there's a cost function involved. If I just don't have time and you don't have time to do it, we'll try and sneak that in with the ALTA. So hopefully this is helpful. I'll see you tonight. I'll put this up right away. Thanks a lot.